All right, let's go ahead and revisit the ice skater phenomena that we watched in the beginning of this video. We're going to solve an example problem with this ice skater. We've been given some data here as well for their motion. We're told that initially the ice skater is spinning with an angular velocity of 0.8 revolutions per second with their arms extended. And as they have their arms extended, their moment of inertia is 2.34 kilograms times square meter. When they bring their arms closer into their body, though, their moment of inertia drops to 0.363 kilograms square meters. And that should make sense, right? Because moment of inertia is a measurement of how far from the center of the object's mass is distributed. And so when the ice skater brings her hands in or her arms in closer to her center, she is distributing her body's mass closer to her center. And so the moment of inertia will decrease. Let's solve for her angular velocity then after she pulls in her arms. And we'll also solve for her rotational kinetic energy before and after bringing her arms in. So because there is no net external torque being applied to the skater, in other words, the only object we have in our system is the skater, and there's no object or agent applying an external torque on the skater, then I know that the angular momentum of the skater must be conserved. In other words, the final angular momentum, right, L final, must equal the initial angular momentum, L initial. If I expand this, I could say that the final moment of inertia of the skater multiplied by their final angular velocity must equal their initial moment of inertia multiplied by their initial angular velocity. I can now rearrange for omega final because that's what I'm solving for, right? Their angular velocity after they pull in their arms. So here omega final would be equal to the initial moment of inertia multiplied by the initial angular velocity divided by that final moment of inertia. And normally I would change my angular velocity to radians per second. However, in this problem, we've been given the angular velocity in revolutions per second, and we're asked for the angular velocity in revolutions per second. So there's no need to convert your units for angular velocity here. So if I plug in my values from the problem statement, that would equal about 5.2 revolutions per second. So we can see quite a bit faster than when she was spinning with her arms extended, right? Almost a good, 6 or 7 times as fast. So let's also now go through the process of calculating their rotational kinetic energy before and after the arm movement. So if we solve for the initial rotational kinetic energy, we'll just call it this. That would be 1/2 their initial moment of inertia multiplied by their initial angular velocity squared. And in this case, because energy is expressed in the unit of a joule, I do need to convert my angular velocity here to radians per second. I can't use it in revolutions per second. And the reason is because radians are essentially a ratio and are allowed to disappear from the equation. Revolutions are not. And so in order for me to get a joule, the radians need to go away. And so I need to convert my angular velocity to radians per second now before I plug in to the kinetic energy formula because I'm wanting my answer in joules of energy. So if I do that, I'll just do that to the side here, right? That would be 0.800 revolutions in 1 second. Well, I know that in 1 revolution, that's going to be 2 pi radians. So I'll just multiply my angular velocity by 2 pi. That's about 5.03 radians per second. And so I'll go ahead and plug that in. I'll use the exact value too in my calculator here just to make sure that 5.03, I'm rounding for example's sake, but I'm using the exact value in my calculator, and I get this. I get 29.6 joules of rotational kinetic energy initially. Now at the end, after they have pulled their arms in, right, that would just be 1/2 times their final angular moment of inertia multiplied by their final angular velocity, and that would be equal to... All right, and please note here that I've multiplied the final angular velocity by 2 pi inside the parentheses in order to convert that to radians. That might be a bit simpler when you're solving this problem in your calculator than doing it as a separate step, because then that way, you won't have to round anything. And so I'm multiplying by the 2 pi just to make sure I'm in the right unit system here. Therefore, my final rotational kinetic energy is 191 joules. Okay, now you may be wondering, where did that rotational kinetic energy of the skater come from, right? How is it possible that they now have more rotational kinetic energy than they did before? Well, in this case, the skater, right, is burning chemical potential energy in the form of calories in order to essentially do work by pulling their arms in, right? That takes energy from the skater in order to bring their arms in close to their body. And so, in order to do that, they are having to spend chemical potential energy stored in the glucose molecules in their body, essentially in order to, increase their rotational kinetic energy. So this is an example of not necessarily work being done if we consider the skater to be their own system, but a change in the internal energy of the system by decreasing a form of chemical potential energy in order to increase their rotational kinetic energy. And this is the exact same as if a person was running essentially and they're burning calories in order to give themselves kinetic energy, or a car was burning fuel in order to spin the axles of their wheels faster, right, in order to go forward and give themselves more kinetic energy. So it's just a reduction of one kind of internal energy for another. All right, and that is an example of conservation of angular momentum when dealing with an object that changes both its moment of inertia and then resulting angular velocity.